Chapter 1, Fundamentals of Thermodynamics, Section 1.5, the Third Law of Thermodynamics. The Third Law of Thermodynamics states that the entropy of a perfect crystal at 0K is 0. There is a slightly different expression. The entropy of a system is minimized at 0K. These two expressions are slightly different. Let me use an example. If you have a diamond at 0K, its entropy is 0 based on the first expression. But based on the second expression, we can only say its entropy is minimized at 0K. But we do not know the absolute value of the entropy of this diamond at 0K. The first expression is more commonly used because it provides a zero reference. We know the entropy value is 0 for this diamond at 0K, and we can use this information to calculate the entropy of the same diamond at room temperature or other temperatures. So it's more convenient in physical chemistry. But Heisenberg told us we do not know the positions and momenta of the nuclei and electrons in a system exactly at the same time. So there's always some disorder associated even with a perfect crystal, even at 0K. So can we say for sure its entropy is exactly 0? I don't know. But it's common to choose a zero reference for convenience in thermodynamics. So it's more convenient to just say, well, the entropy of diamond is 0 at 0K. And let me give you two other examples about zero references. We learned enthalpy, we learned Gibbs energy, but we will never know the absolute value of enthalpy or Gibbs energy of any object in this universe. Because they are relative quantities, we have to set some zero references first. So for convenience, we say this: at room temperature, the standard enthalpy of formation and the standard Gibbs energy of formation of pure elements in their most stable states of aggregation are set to 0. For example, if you have 1 mole helium gas, 1 bar pressure, and it's pure, and then at room temperature we say its standard enthalpy of formation is 0, its standard Gibbs energy of formation is also 0. And based on this information, we can even calculate the standard entropy of formation for helium at room temperature. This is because H is equal to G plus Ts. That's the definition of Gibbs energy. Gibbs energy is enthalpy minus temperature times entropy. So we can use this derivation to get this standard enthalpy of formation is equal to the standard Gibbs energy of formation plus the temperature times the standard entropy of formation. At room temperature, T is 298 K, and for this pure helium gas at 1 bar pressure, its enthalpy of formation is 0, its enthalpy of Gibbs energy is 0, therefore its entropy of formation is also 0. But again, based on the third law, we say, well, if you have a perfect helium crystal at 0K is 0, but over here it says, well, the entropy of formation of a helium gas at room temperature is 0. Which one is correct? Actually, both are correct. It's just because we used a different zero reference. Over here we say the helium crystal at 0K. That's the zero reference. When we talk about the entropy of formation, the standard entropy of formation, we actually use what? We use pure elements in their most stable state of aggregation. We use room temperature. We use this as zero reference. But again, I mean, no matter which zero reference you choose in your calculations, in your derivations, please make it consistent. You just choose one set of zero references and stick to it. Again, the third law of thermodynamics states that the entropy of a perfect crystal at 0K is exactly 0. Again, this is more commonly used in thermodynamics. So for now, we'll stick to this expression. Now here's an example problem. Determine the entropy difference between 1 mole diamond and 1 mole graphite at 0K. So first I want to show you the structure of graphite. So those are carbon atoms. This is a graphene sheet, and there's another graphene sheet. There's a distance between the two sheets, about 3.6 angstroms. Over here, this is the structure, molecular structure of diamond. They look quite different, and these two have different density values. They have different molar volumes. The density of diamond is higher than the density of graphite, so that means the molar volume of graphite is greater than the molar volume of diamond. Can we just say, well, in this case, can we say the energy is more dispersed in graphite, and then graphite has a higher entropy than diamond? Well, the answer is no, because both diamond and graphite, they have a 0 entropy at 0K, and therefore the difference is 0.